Apologies, we having a little trouble getting the computer to show us our PowerPoint thing. Okay, today we're the music. Why Hebrides Overture? To me, it sort of sounds like flowing things and moving and action, and that's the theme here, where we're going to see that. With magnetism, you have to have things moving. We have to have charges moving with some velocity. Or, in other words, we have to have currents with some length of them. In order to get magnetic fields, there seems to be currents every time. And the other feature is that we're going to move on today, I hope, to the idea of induction, where it turns out that, again, interestingly, you see, this idea, as first demonstrated by Ørsted, by having a current, he produced a magnetic field, or magnetic influence, we call it a field. When he did that, the natural question was, can you turn it around? Can you maybe use magnetism to get electricity? I mean, this is, if you were a scientist at the time, I would hope that idea would come to you. And people started looking for that. In other words, the inverse effect. How do you start with a magnetic field and maybe get current or voltage? That would be a great trick, because they knew how to get current and voltage by Volta's method, namely batteries. That was known. So you could get currents with Volta's battery cells, but that has its limitations too. And the question was, is there a way you can go? Now that you see there's a connection between magnetism and electricity, is there a way that you can get electricity out of magnetism? So people started searching madly for that. Here's my, well, I'm going to put this away till later. But this will be the electromagnetic induction. The thing crashed on me the last time, though, at this point. Huh, what's going on here? Weird. PowerPoint has an error. I don't know what's going on, friends. Let me, okay, so that's what we're going to get to hopefully today, and that is the idea what is this machine up to? I can't even find the arrow. It's really dead. Oh, here we go. Something's. It's unhappy. Well, we're going to hopefully get to this point of what's called electromagnetic induction, which is the way that was found to make this connection. That is to go from magnetic fields to currents. But the trick is, as in the Hebrides, you have to have a moving or varying magnetic field. That was the trick. You have to have a moving or time varying. Here, so it's all motion. Motion is involved here. And if you have that, you're in pretty good shape. I wonder if I can, this is still unhappy, huh? Gee. I don't know. Well, let me carry on. Let me call James, and maybe he can fix that while we talk. James, I still have problems with the, the PowerPoint seems to be not working. Okay, we'll just go on. But first I wanted to finish up some things that we began, still talking about magnetism. We had figured out that there are ways of using the currents to find the magnetic fields at a distance r in various situations. We were able to solve ourselves a few situations, namely using the Biot-Savart. It's the analog of the Coulomb law. That is, you have a charge of some sort, electric or magnetic, and the field goes as 1 over r squared. So you get a field. This is the general pattern. A charge over r squared, and then you have some constant in front. In the case of Coulomb, the constant in front was k, which is equal to 1 over 4 pi epsilon naught. And in the case of Biot-Savart, the constant in front was mu 0 over 4 pi. And in the case of Biot-Savart, the charge was either QV or I times L, which was the thing that's sort of creating the field. In the case of Coulomb's law, the charge was what we call charge. The complication was that here you had that cross product between the V and a unit vector to the place you're interested in. And here, the Q produced a field right in that direction. So that's the main thing. But the beauty part is that it's the same kind of structure. If you can remember that structure, you're okay. The other way we had to find the field was Ampere's law, which was kind of an integral situation where if you have, in the case of Gauss, if you can integrate the field over the whole surface area of a closed surface, E dot dA, you're guaranteed to find the net charge inside over epsilon naught. In the case of magnetism, we could find by the so-called Ampere's law, if you have a bunch of currents pointing every which way, whatever, if you make a loop enclosing those currents and you multiply the B times your distance around the loop, so it's B times your little element dl, you multiply that, go all around the loop, it will guarantee you to find the net current inside, and you'll have a mu 0 on top. Again, that feature. Okay, so in special cases, we could actually find the E from this trick, and in special cases, we could find B by this trick. We did, for example, the solenoid by this method, and what looks like a pretty hard problem you can solve with the Ampere law. Okay, so now this tells me how to find B in some cases. And in other cases, the problem will be they'll even just tell you what B is. So given B, what do you do with it? Well, again, we have the same analog of the electric case and the magnetic case. That we find the force on one of these elements that we talked about. They create the field, and they are acted on by the field. One set creates the field, those are the pushers, and then you have the people that are acted on, since the pushees. The force here was given by Q times the electric field that you created electrically. And this is the field caused by one set of charges, and this is the force of 1 on 2. So I have charges 1 create the field, and I put charge Q2 in here. Very important idea that you segregate who's causing the field and who's being acted on. Same thing here. The force will be one of these magnetic charges times the B field that somebody else created. So this will be the force of 1 on 2, and this is the magnetic charge that's being acted upon. So it could either be I times L or Q times V. There are two different things. In any case, it's a moving charge. Current times a distance, the length of this element, current element, or Q times V. And the complication, again, is this cross product thing. So the force is given by that cross product. And that's pretty much the whole story. It's similar but different, a little bit harder. Now, I wanted to do a few examples of, we did a few examples of how you make the field. Now, assuming you've made it, let's do a couple of interesting problems to see how you use the field. Suppose somebody tells me I have B. How do I use that to do something nice? Well, one of the nice things I would do, let me do it here, is, as I showed you last time, you can make a motor. We made a very nice motor. See what that thing went last time? It was really crazy. But the essence of the motor is that, well, let's see. Do I have one here? Ah, yeah. Very similar. Here, this is not going to be, yeah, this is the structure of a motor. We're going to use it for other purposes. The idea is you have a coil and you have a magnetic field, these two magnets. In a motor, you put current into this loop, have a battery. So you have to put energy in to get action out. You don't get it for free. You put in current through here. We had a battery before. Now, this is a loop of wire. The current flowing through this produces a magnetic field in here. Are we working, friend?
It's working. I'm just going to hook you up.
Oh, okay. Oh, okay.
Now it's connected.
Yeah. Well, it's a generator. It's acting as a generator now. Sure. Now, so let's think. So the idea is that you have a loop of current. Let me try to symbolize that loop by let me make it a square loop rather than a circular loop, just for sake of argument. A square loop that looks something like this. There's a reason for this madness. And that is put in a magnetic field. Let's say north, south. So that my magnetic field is running this way. Okay? Now, the point is, I put current into this by having, let me do it this way, a piece of metal which is attached to here, and I have a piece of metal which is attached to here. And then I have here brushes which are touch this but slide, and I put a battery on here. Let me try to get the direction. Well, we'll see how it goes. Now, the point is that when it's like this, with a plus here, current will flow through the loop, and let's see, how do I indicate a brush? It's just a brush. that touches this metal contact. Now, the direction of the current is like this. Okay, so if the current flows up through here, now this, I don't know if you can see this, but I'm trying to get a loop that's going into the blackboard, and current is flowing through the upper arm in that direction into the blackboard. So let me try to indicate that by a typical convention arrow like that. Is that okay? Going in. So the current is flowing this way, in here. So that's my I, and B is this way. So the force on this loop, at this juncture, I cross B, the force is downward. Is that what I want? I tell you what. Let me change the sign of the battery. Sorry about that. Let's put it this way. And let me change the sense of this current. I'm sorry about that. So if this is the plus side, the current will be going in here, coming out here, coming through here. So the current is this way. Right. So the current is this way. Current times field, the force is upward. So what's happening is this is on an axis. The loop is being turned this way when the current is in this direction. So that's how I get force on this loop, to see it spin around the magnetic field. Now, the slightly tricky part is that when the loop reaches vertical, let me try to draw that. When it's going in vertically like this and down, and this part when this reaches vertical, I want the thing to keep going this way. I want this motor to keep going. If that force still keeps pulling up, it's going to stop me from going. So what I have to do at this point is change the direction of the current. To change the direction of the current, I don't change the direction of the battery, but I have these contacts. So that whereas this right side, the plus side of the battery, was touching the yellow contact, at this point, the yellow contact it's hard to draw this, but see, this is coming around. The contact of the plus side of the battery, when this comes around, it touches the blue side. And this one touches the yellow side. So that means that when the loop has turned to this angle, see, it's going this way. When it turns to this angle, what's happening is that the blue side, is now contacted to the battery, and the negative side is contacted to the other side. So what this does for you, it sends the current in the blue side. And the blue side current going into the blackboard is going that way. The magnetic field is still this way. Now you see the force V cross V into the blackboard, cross the field going that way, means that the force on this arm here is downward. So you see, on this side, the force on the blue side was turning it upward, and when you get over to this point, by having switched through these, what's called a commutator, the force has switched to pushing it this way. So it continues the motion. That's how a motor works. I don't want to dwell on it too much, but that's the clever way they figured out that you put current in through a battery, and it will make the thing turn, and you have a motor, which is, of course, very common. I mean, cars have them now, electric motors. A battery-powered car, that turning thing could be your wheels. That turning thing could be a motor in your refrigerator, and on and on and on, electric motors. The other, okay, oh, how nice. Oh, he gave me a different computer. That's how he solved the problem. I don't have to work this. Wonderful, okay. Okay, so these are all our slides on how to make the field. Now, how to use the field. As I say here, the magnetic charge is either a length of current or a moving charge, and we have this law that if you have current, this is the third of our right-hand rules. Right-hand rule number 3 is the one I just used. I hope you noticed that. The right-hand rule is that the force is given by IL cross B, or this charge could be Q times the velocity cross B. Now again, to help me remember it, I usually write it this way: women's lib, LIB. And the point being that if you have a current in this direction and a field at right angles to it, B, you turn I into B, which will give you a force into the blackboard in this case. B will be into the plane, if you will. Okay, you just want to know that. And that is our right-hand rule number 3. Okay? And that's what I used to find the force on the loop as it was going around. Here's right-hand rule number 3. Now, you can apply that to the loop in detail, and what you'll find is that if you have a loop and it has a certain area, we can assign to this loop a magnetic moment, a magnetic dipole moment of the current that flows through it times the area. This is a useful formula. We talked about this a little bit before. Yesterday, we did a circular loop, and we found that the field of a circular loop of current passes through the loop, goes and looks like a dipole at large distances, but inside the loop, it goes. I'm trying to make a loop that's coming out of the blackboard like that. The field comes through the loop and goes, and at far distances, it looks very much like that of an electric dipole, or very much like a bar magnet with the north pole where the flux is coming out, and the south pole where the lines seem to be coming, we say they're coming in. North and south is pretty arbitrarily determined, okay? So the point is that without showing it in detail, if you go through an argument like this in detail, you will find that the field B acts upon a loop that has a magnetic moment. Let me get it right. The current would be going this way to produce a moment like that, where this is the North Pole, okay, and the current is going this way. If you put that in a magnetic field, let me put the field this way. Let's see. Actually, B. So there is a turning moment on this. Yeah, let's see how it goes. Mu cross B. Another one of these cross products. Where this is interesting. If you have mu cross B, then the torque is coming out of the blackboard in this case, because my thumb, I turn mu into B, and the torque is coming out. That represents a motion, a turning about the. That's another one of these strange things. The torque is a turning motion. And so the direction in which it turns is the direction your right-hand fingers turn when you're pointing your thumb in the direction that we call the torque. So in other words, this cranks this around. What this will do is turn the loop in this direction. It will exert a turning moment about that axis. If you put this moment in a field in that direction. So actually to find what a loop will do, it depends on its shape. The easiest thing is just to take its area and the current and just say that will produce a magnetic moment, and it will be turned in a magnetic field. Or you can add up the forces on each of these things, on each of the arms of the loop. In the case of a rectangular loop, it's pretty easy to do. It's much harder to do with a circle, because here the force is pretty much uniform, so you'll have a force, say, going that way, and another force going that way. And the thing, you can sort of get the forces from IL cross B, or my usual LIB. But you have to know what L is. And in a circle, that's not so clear what the length is. But here it would just be one of these lengths here. So that's something actually is pretty well described in the book, or in this slide, where you can see how, from the size of the loop, you can represent the forces that are acting in the first line here, and you can see how they multiply by a length to give you a torque. A torque is also given by R cross F. I don't know if you remember that from 8A. That's an 8A concept. It turns out that you can use that idea to say, I have the forces on this and I have a radius arm. The force is going to turn about that radius arm. So you can, and it ends up being mu cross B. Okay, so with that, you can explain, or either by saying the loop has a magnetic moment because I put a current in it, and that magnetic moment is turned by the torque of the B field on it, or I can say there's a current flowing. Because of the current flowing in a field, there's a force on that current, and the force causes the current to turn. Those will give you exactly the same answer. It's just two different ways of saying pretty much the same thing. I hope you got that. Oh, by the way, one source of error is that in the text on page 451, he does show a motor, but it's rotating in the wrong direction. Actually, it's not rotating in the clockwise direction. It should be rotating in the counterclockwise direction. Why don't you check that at home and see whether you agree with the book on this? I don't. So it happens among friends. Yeah. Also, you can figure out what the energy of a dipole is, because in order to take a dipole that's aligned along the field, which it will, because if this is a north and south, if this is a north and south seeking pole, let's take an ordinary dipole, like a bar magnet, and if you put it in a magnetic field, what you mean by that is that the north will want to go along the field, the south will want to go down the field. Because where this came from is that there was a north over here, and there was a south over here someplace. So that means that the norths are going to repel each other, and the south is going to be attracted. In a case like this, the dipole will line up with the magnetic field. I hope that's a very good idea. In other words, if here's your field by somebody else, eventually this thing is going to want to line up this way, right? Along the field. That's what your compass needle is doing. It's lining up with the Earth's magnetic field, and that tells you which is north. Okay, so, but if I take this and I turn it around, I have to put some work into this. In other words, to do this, I have to pull that north against the B field, and that puts work into I do work against the field, and I store energy here. I store energy in this because I let it go. It'll go boink, right? So I've stored energy. And the stored energy is mu dot B. So it's a potential energy, but it's a dot product. It has to do with the angle that the magnetic moment takes with respect to the magnetic field. So that's another interesting feature. Okay, what else do we have? Oh, well, as I said, the other type of magnetic charge, you have the current. We've just dealt with a current line in a magnetic field, and that produces a force. But also, we can replace that current line by a charge, a point charge, Q, with a velocity, V. That also acts as a source and also acts as a pushee that can be pushed on. And you just substitute for the Li, QV. And you get the equation that I have about down at the bottom, NQV, or finally QV cross B, which looks very much like Li cross B. And that was called the Lorentz force. And again, it's a vector product. And that one we've actually demonstrated a few times in the class with some of the models we have here, where I had a tube and I had electrons shooting across, and I brought my magnet over here, and I had a magnetic field going in, and the electrons were going, the magnet was this way, and the magnetic field into the blackboard. And when I brought it nearby, the beam deflected. So here's a beam of charges, and there's a sidewise force. So if the field, let's say, was north to south, so that would be this way, and I forget exactly which way the current was, but let's just make it up electrons going this way, so the current is actually going that way because electrons are negative. So we have I cross B. The force will be upward. In this case, the beam will deflect upward. I think that's actually how it was, in fact. So the force will be upward, and the beam will go upward when it passes through the magnetic field. So, in other words, this force law works perfectly well with individual point charges, and it's used, well, here's some examples of how to do that. You see, the point being in the left-hand diagram there, A, you have to have V and B because of this cross product. That the force is equal to the charge times V cross B. The cross product involves the sine of the angle. So you want the sine of the angle to be large to get a large value. If they're parallel, you get no effect. So if the charge is going along the line, it won't feel the field. But when it's perpendicular to when the velocity is perpendicular to the field, then you get the force in the third direction. And also it depends on the sign of the charge. You see, as shown in these pictures, plus charges will do one thing, and if the Q changes, the force changes. This computer doesn't like it's all strange. Okay, so there's the Lorentz law again, V cross B. And we did this experiment, actually, bending things. Now, I wanted to say a word or two about the instrument that you used in the lab to measure magnetic fields. I don't know if they used the word a Hall probe. Did they use that word? Yeah, Hall probe. Okay, so that's the Hall effect, named after an American scientist named Hall. And very quickly, I wanted to show you how that works. If you haven't seen it, it's actually in the book, but maybe not too clear. Let's see. Oh, I'll use the way the book does it. What you have is a slab of material. Typically, it's a semiconductor of some sort. And let's see. He puts the magnetic field this way. The whole thing, so, yeah. Okay. Now, what you do is you pass a current through this. So you put a battery on this way. So now you're passing a current through here. Right? Now, this is conventional current going from plus to minus. Now, again, you have, if you can think of it, it's individual charges, the little Q's. Maybe I'll stick with this. Q having a velocity V along the rod, but the magnetic field is that way. So the if I turn V into B, I get a force perpendicular to the 2, which will be in the direction upward. Right? Yes, question. V is not voltage, it's velocity. QV. This is little v. Good question. There's going to be there's two different voltages going to happen here. One is the voltage you put on to make this current go at a speed v. The charges are moving at a speed v. Because they're moving charges, and you have a magnetic field this way, there'll be a force that way, which is going to force the current upward, sort of like we did in that demo where we had a beam of electrons and I put a magnetic field. and the beam deflected upward, the charges are going to deflect upward. Now, so there's a force that way. The nice thing about the Hall effect is that it can distinguish between positive charges moving. These would be positive. This is the conventional current with positive charges moving. If you do the same thing with the same battery, but if the charges are negative, look what happens. The conventional current is this way, but the actual velocity, because these are electrons, you have electrons going that way. So with the B field in this direction, you have, again, QV cross B. V is that way. The field is that way. So the force is downward. Force is QV cross B. But the sign is, is negative. So the force is, no, V cross B. V cross B is downward. But the force, QV cross B, is upward. The force is upward. So what this does, it moves the minus charges up here. The minus charges go to the top because the force on them is upward. So you have a different story. What happens then, if you were to measure the voltage from this side, put a voltmeter here, that's another voltage that's in the picture. This is the voltage applied to make the current flow. That we leave constant. But the Hall voltage is the voltage across the plate between here and here, V Hall, which is the crosswise voltage. That will change sign because you'll have negative on top if you have negative carriers, and you'll have positive on top. So it can tell the difference between positive and negative carriers, which actually exist in nature. I think I have to stop there because I do want to do one more thing with you. Let's see if I can escape. And if I can find my other thing, wherever it may be. I don't even know where it is anymore here on the new computer. But I want to move on today just to introduce you to the quick idea, this one, namely that we're going to get, how do we get electricity out of magnetism? And this was the induction effect, which is credited to a very, very great physicist, chemist, all-around terrific person, Michael Faraday, in England. Ørsted discovered his thing in 1820. By 1830, after scrambling around and trying to do this thing, use magnetism to create electricity, Faraday finally found how to do it. And it was very hard to do because, of course, he had no instruments. They had no electrical instruments. How do you do this? What we do is very simple. He's changed it. Okay. Sorry, folks. For us, it's pretty easy because we have these wonderful electrical equipment that has been developed in the centuries since. Not very clear. Okay. what he did brilliantly, well, and how he discovered it, you have to take a magnet, you take a coil, and you do changing the magnetism inside the coil. And this is generating electricity in here, which is being picked up on this meter. So that's it. That discovery is how we generate all the electricity that we use these days. We have a changing magnetic field. That's it. Now, how do we do that in real life is changing the magnetic field. Well, there are several ways of doing it. The way we're going to do it today is we're going to take a loop, again, one of our loops. We're going to put it in a magnetic field, steady magnetic field, and we're going to turn the loop. And turning the loop means that the amount of field flux. See, the idea is it's, again, one of these concepts of field times area. It's a flux. Magnetic flux is the field times the area. It's sort of like the same with, we had an electric flux. And if you can change the flux through the loop, you'll generate a voltage across the loop. Now, I want you to, this is a very important experience that I want you to have. What I'm doing here is I'm turning loops inside a magnet, and I'm generating electricity. Oh, I'm sorry. I did it the wrong way. I have to go counterclockwise. Sign right here to remind me. And tighten the ship down. Okay, here we go. So, now I can do this. Now, I want each of you, before you leave, to try this, because this will tell you what the world's problem is, turning that handle. The difference is, and another interesting thing, when counterclockwise, meaning this way. Yeah, please do it counterclockwise. Don't be like high ones. It's very easy when you're not generating current, but when you start to pull current to light the bulb, it becomes quite hard. So I want you to try it and feel, because then I want you to imagine lighting up a whole city, turning the handle like this. Why don't you come up and try? This is an experience of a lifetime. You really have to know that, and before you leave, try it. Oh, the other thing you can do, you want to see braking, you see this counterclockwise. If you do this, and you pick up speed, it goes okay. But then if you draw current, it stops. This is what the Prius does. Your wheels go fast. When you put on the brakes, you attach the wheels to a generator, and it charges your battery because it's turning, and the energy here goes into charging the battery. But I want you to try this, please. Be gentle, but come on. This is a very important idea.